Welcome everybody to the Pattern Recognition Symposium. My name is Andreas Meyer and I would like to show a presentation to you by Philipp Klumpp, and it's entitled Detection of Surgical Masks and Their Impact on Speech Signals. Philipp, very much looking forward to your presentation.
This is about a topic that we are all very familiar with. It's about surgical masks. Wearing face masks in general, I mean, everyone got quite used to that right now. The challenge was to detect the presence of surgical masks in very short snippets of 1 second audio. They were recorded from 16 female and 16 male speakers. It's German. It's around about 10 hours of recorded German speech. And the baseline unweighted average recall was 71.8%, just to give you some intuition of the difficulty of the problem. I do a lot of phonetic analysis, as many of you might already know. So just as an introduction, what is a phoneme? A phoneme is a basic sound of a language, and if you concatenate a couple of phonemes, you say a word. I'll come to that later again. Our hypothesis was that if you wear a surgical mask while speaking, this will affect the way certain phonemes would be produced. So, well, we have 10 hours roughly of data available from the challenge. That's not as much. Can we maybe do transfer learning and use approaches that we have already used before? Idea is to train a German phoneme recognizer from a larger corpus, then create phonetic labels for the whole data set of the challenge, and then train a secondary recognizer that is able to differentiate for every phoneme whether it was produced with or without a surgical mask. So step one, we need a German phoneme recognizer. For this, I will just give you a brief overview over the recognizer. I could talk like half an hour about this. It was created or trained with a German Wertmobile corpus, which is comprised of around about 29 hours of recorded dialogue speech, 307 female, 286 male speakers. So you see we have a lot more speakers in here already. We increased the amount of data as well by randomly adding Gaussian noise with different signal to noise ratios, and increase our robustness with this, the robustness of the recognizer with this approach. What features do we use? First of all, we did some audio pre-processing, root mean square normalization, a DC offset removal. Then we compute 2 spectrograms, each of which have a window size of 25 milliseconds and a step size of 10 milliseconds. And they were both filtered with a MEL filter bank with 256 frequency bands. So the first MEL filter bank is a regular MEL filter bank. As you can see down here, we have a very high frequency resolution in the lower frequencies and a coarse resolution for the higher frequencies. The idea is to basically resemble the human perception of frequencies. As well, we added an inverted MEL filter bank to compute the second MEL spectrogram. So final input to our network will be a dual channel result. I will come back on that later when we see the results. What does the neural network look like? Well, we have a CNN-RNN combination to give us frame-wise phonetic posterior probabilities. We are able to detect 31 different phonemes, 1 phoneme for silence, and 30 other phonemes that are comprised in German speech. We have an initial convolutional stem just to reduce the amount of frequency bands in our input. We then have adapted inception blocks to operate on a time sequence, which are our main tool for the feature extraction. For temporal analysis, we then have a stacked layer of 2 bidirectional gated recurrent unit RNNs. And in the end, for every time frame, we perform a dense layer down to 31 phonemes and map this to a probability density function. So this recognizer was trained. Very brief intro of the results. We have an average, or we have a final phoneme error rate of 17.9% per frame, which is quite close to state-of-the-art methods. Step 2 that I talked about, now that we have a phoneme recognizer, we would like to create phonetic labels for the challenge data. I already told you we have 31 different phonemes, 1 for silence, 30 remaining phonemes that describe German. We have to split those phonemes up, as you see in the bottom here. So the 30 phonemes could be produced either without a surgical mask or with a surgical mask. With this knowledge, we increase our label space from 31 to 61 dimensions and basically create a new phoneme recognizer with this. What did we do? We conserved all the feature extraction part from the Wertmobile model, because that is pre-trained, that is knowledge about how to extract valuable features for phoneme recognition. What we ended up changing was only the stacked bidirectional layer and the final dense classification layer. We also introduced dropout of 60%. Sounds like a lot, but it greatly helped to give us overall a more robust solution. How do we end up now? Remember, 17.9% was the phoneme error rate initially. Now that increased drastically to 45.1%. So only a bit more than half of the frames is correctly classified. But we have to keep in mind that it's quite hard to distinguish for every phoneme, not only detecting the correct phoneme, but also predicting whether this was produced with or without a mask, which makes this task, a lot more challenging. Short overview of the results. We create a 154-dimensional functional vector for every utterance in the challenge data set. And then with a training set, we create a random forest classifier with 100 trees. And we achieve an unweighted average recall on the development set of 70.8 and on the test set of 75.4%, which is already outperforming the baseline architecture, which is basically an ensemble of multiple feature and representation learning techniques. We have the advantage we can not only outperform the baseline, but we can also extract more knowledge about the overall problem. What we did is we extracted the intermediate feature maps, which is a 512-dimensional vector after the inception blocks. We assigned every of those vectors to one of 8 phoneme groups. So you can group the 30 different phonemes to groups. And for each group, we then performed a PCA to map the 512-dimensional vector down to 1 dimension. Very straightforward. And then we fit a Gaussian distribution once to the representations of the clear samples and once to the representation of the mask samples. And then we try to identify whether there's differences in these Gaussian distributions. Let me tell you, closed vowels, open vowels, and voiced plosives are quite simple examples where you can see there is almost no difference visible. Vowels are A, E, O, U, all those. Voiced plosives are B, D, and G. So you might also refer to them as soft plosives. However, if we look at the phonetic analysis results for fricatives and unvoiced plosives, we can see that there is a significant difference. We tested for significance with a t-test. Fricatives are sounds like sh, and unvoiced plosives are p, t, k. So why do we observe this difference? Well, all these sounds, all these phonemes require you to produce some sort of airstream through your mouth. And if you have an obstruction right in front of your mouth, this will definitely affect the way the phoneme sounds like. I mentioned in the beginning we used an inverse null filter bank, which gives us also a high frequency resolution in the higher frequencies. And this was particularly helpful here in this step because we could basically conserve information in the high frequencies that was necessary to distinguish between clear and masked speech. Then come to a conclusion. So what we did was basically an acoustic transfer learning technique to learn about phonemes and phonetic recognition from a large German speech corpus. We transfer that knowledge to the challenge data and then analyzed the challenge data and the speech from clear and masked representations to also give insights on how a surgical mask affects the speech signal. Thank you very much for your attention. That's it from my side. If you have any questions, go ahead.